In this section, we're going to look at general solutions of linear equations. What does that mean? Well, basically, we're going to be extending what we did in section 2.1. You'll remember in section 2.1 that we specifically looked at systems that had a single unique solution. Okay, everything that we had ended up having a constant value for x, y, and z. There was just one value that you could have for each variable and everything could be solved. What we're going to look at here is particular systems where you can end up with infinitely many solutions or no solutions and what those systems look like. And if you were to perform this Gauss-Jordan method on these systems, what do we need to look out for to show that we have no solutions to the system, and what do we need to look out for when we use this method to show that we have infinitely many solutions? When we went through Gauss-Jordan, we had this step-by-step process where if we had it in matrix form, we would make sure that our top left element always was 1 when we started. That would mean that our coefficient of our first variable was a 1. Then we would eliminate that variable from everything below that first equation. So we would make all the entries in the matrix below that 1 a 0. Then we would go to the second variable in the second equation, which in our case, in our last example of 2.1 was a y. We would then say, okay, we want a coefficient of 1 for that second variable in our second equation, and then we're going to eliminate that variable from everything below the second equation. And we went through this step by step. So you ended up with almost this diagonal left-hand matrix, where you had ones on the diagonal, and then you had this other column at the end, which was the constants. They were the values of each one of our variables. When we went through this and we turned each one of those diagonal elements into a 1, and then we eliminated everything below it and eventually above it as we went through backward elimination, that is something called pivoting. Okay. You pivot around those entries. So pivoting is where we went through and we turned each entry, each diagonal entry for our last section into a 1, and then we made each entry below it and eventually above it a 0. So this is what we did in our last section. As I said, we in this section are looking at systems where we may not actually end up with a diagonal matrix. We may not end up with a system that looks exactly like what we had in section 2.1. It's going to end up looking slightly differently because we're going to be looking at things that don't have a unique solution like we had in section 2.1. When we pivot in this section, in general, what you want to be looking for is to pivot around the first entry in the first column, the second entry in the second column, third entry in the third column, etc. Sometimes that is not possible and you have to skip to the next entry because there is no entry there for you to pivot around. Even if you were to go through our elementary row operations and swap some of these rows of the matrix or our equations equivalently around, you cannot actually pivot around that point. So you may have to skip over to the next column or the next entry in the matrix. So in general, what we like to do is to pivot around, quote unquote, the diagonal entries as much as we possibly can. But there may be cases where we cannot do that. In that case, if there is no term, if there is no pivot in that particular column, in that particular entry, and you can't get one in that entry from switching that particular row with another row below it that hasn't yet been dealt with. If you cannot do that, then you have to say, okay, we then have to pivot around the next entry. But for the majority of the time, you are going to be trying to pivot around those diagonal entries. I'm going to go through an example to kind of show you what these look like, because that really helps when we are doing this. This first example is going to be a system that has no solutions. Okay, this system has no solutions. I'll tell you that now, and we can go ahead and look at y. So our system is going to be x minus y plus 3 times z is equal to 3. And then we're going to have negative 2x plus 3y minus 11z is negative 4. And x minus 2y plus 8z is equal to 6. What I'm going to do is go ahead and put it in matrix form and do the first couple elementary row operations on this. Like I said at the end of the 2.1 video, you can use a calculator to do this unless I specifically say, hey, I want to see you use this Gauss-Jordan method by hand. But otherwise, if it is a homework problem and they don't specifically ask you to go through the whole method, you can use a calculator or even just use a calculator to check your work at the end. So the matrix for this would look like this. Okay. We've already got a 1 in our top left-hand entry, so we already know that we can go ahead and pivot around that entry. It's not a 0. It's only if you come across a 0 in a pivot entry that you really have to worry about it, and then you have to pivot around the next term over. But here we have a 1. We don't even have to divide our row or our equation equivalently through by anything. It's fine as it is. Now I need to make the entries below it a 0, so I need to make the negative 2 and the 1 a 0. So to do that, for my second row, I'm going to add 2 times my first row. And for my third row, I'm going to subtract my first row from it. So I'm using that pivot term to eliminate or to make 0 my negative 2 and the 1. And remember, you do it to every entry in that row. So you use, for my second row, it's going to become my original second row plus 2 times my first row. So I'm going to get my first row remains the same. My second row is going to become 0, 1, negative 5 and 2. My third row, I'm going to subtract my first row from my third row to make that a 0. And then I get negative 1, 5 and 3. Okay. Again, I'm very fortunate in this case. My pivot this time is going to be this entry. It's my next diagonal entry. It's my second term in my second column. Okay. So I'm going to go ahead and pivot around that. It's already a 1. I don't have to divide my row through by anything, but I need to make the entry below it a 0. So to do that, I'm going to add my second row to my third row. My first 2 rows remain the same. And I end up with this matrix. At this point, you would think, well, you carry on, etc., etc. We have a 0 in our next pivot entry. Can't pivot around a 0 because we can't turn it into a 1 in any way. There's no way that we can pivot around it. And we don't pivot around a non-variable column. We don't pivot around this end column. They're just constants. So at this point, we're done with the forward elimination. But I cannot do any backward elimination that is any use to me at this point. I could go ahead and turn this entry here into a 0. But it's kind of pointless given what I have for my last row. And this is something that you need to be aware of to look out for. If I look at my last row, if I were to turn that back into an equation, I would have 0 times x plus 0 times y plus 0 times z. So my whole left-hand side is a 0. And my right-hand side of my equation would be 5. That tells me 0 equals 5. Evidently, that's not true. So that tells me I have an inconsistency here. So because my system is inconsistent, it means I have no solutions. So if you ever come to a point in a problem where you get this inconsistency, there is always no solution to the problem. So always look for all zeros on the left-hand side on a particular row and a non-zero constant on the right. That tells you that if you have a row that looks something like this with all zeros on the left and a constant that's non-zero on the right, it means that there is no solution. So what does that mean for us in terms of if we were to graph this? We have 3 planes here. It means they don't intersect at any point because you can't solve it. In our section 2.1, it had a unique solution. That means that they intersected at a particular point. Here, they don't intersect whatsoever. Now I'm going to move on to another example that we need to be aware of, which is when there are infinitely many solutions. Okay, so the example that I'm going to give this time is going to be x plus y plus z equals -1, 2x plus 3y plus 2z is equal to 3, 2x plus y plus 2z is equal to -7. Again, I'm going to put this as a matrix, so go row by row and look at my coefficients. Okay. Again, here I am very fortunate. I have a 1 in the top left-hand corner. That means that I don't have to worry about dividing that equation through by any non-zero constant, or I don't have to swap 2 rows or anything like that because my first equation has a first variable with coefficient 1. So we're good there. Now I need to make the elements below it 0, so you're going to do row 2 minus 2 times row 1, and you're going to do row 3 minus 2 times row 1 to make both of these 2's into zeros. So if I do that, you can go through this with the Gauss-Jordan method. You should get this as your matrix. Okay. Again, very fortunate, we have a 1 in this position in our second variable, in our second equation, has a coefficient of 1, so we can pivot around this, but we don't even have to divide through by any non-zero constant. It's already a 1, which is great, and we don't have to swap anything. It's fine where it is. So now I'm going to make this term in row 3 a 0 because I want to make everything below a pivot a 0. So I'm going to do row 3 plus row 2. And when you do that, your matrix should look like this. We have actually run out of pivots here, okay? We don't have a pivot in this third column, okay? Because my next entry, I would be looking in the third row. I've already got a pivot in rows 1 and 2, so I would be looking for a pivot in row 3. Well, I've got all zeros on my left-hand side, and we know we never pivot on our last column anyway, but we don't have an inconsistency here, because from our last line, we literally get that 0 would equal 0. That's consistent, so we're fine with that. But we have one less pivot than we do variables. That's fine because our system isn't inconsistent, but that's actually what's going to give us infinitely many solutions. So when we're going to carry on with this, we know we can do backward elimination here. We don't have to stop like we did last time because our system is actually consistent. Now, the thing that we have to be aware of when we do backward elimination, we've got no third pivot in this case. That's fine, but when I do backward elimination, I also have to worry about my second and my first pivot. So for my second pivot, I still have a non-zero entry above it at this point. So I need to get rid of that and make it a 0. If I do that, I'm going to do row 1 minus row 2. That's what's going to make it a 0. And I should get this matrix. And that's as simple as I can get this. I've done full forward and backward elimination here. What does this tell us? Well, whenever you get to this point, my suggestion to you would be always write it back out as formulas so you can actually see what is happening now that you've fully simplified it. From our top row here, we would get x plus z is equal to -6. Okay, and from our second row, we would get that y is equal to 5. And we don't get any extra information from our third row because that just tells us 0 equals 0. We already know that. So we don't have any new information about our variables from our third row. Whenever you get this kind of situation, we actually end up that y has a specific value. That's fine. If you ever have a column that doesn't contain a pivot, which in this case would be our third column, we say that that particular variable that corresponds to that column is a free variable because it can equal anything it likes. It has no constraints. So we say that any variable that corresponds to a column that has no pivot in it is a free variable and it can equal any value that it likes. Why do we not have a pivot in that column? That's something that I want to make sure that we all understand. Why do we not have a pivot in this column? A pivot is always the first non-zero entry in that particular row. Okay? First non-zero entry in a row. So we have a pivot here. I'm going to change colour here actually to make sure that we know where it is. We have a pivot here. We have a pivot here. Okay? This term here cannot be a pivot. That one can't be a pivot because it's not the first non-zero term in a row. So that's not a pivot. So we do not have a pivot in our third column because a pivot has to be non-zero. You can't pivot around something that's 0 because you can't make it into a 1 and you can't use that particular value to make everything below and above it a 0. So we don't have a pivot here and we cannot use anything on our right hand side as a pivot because they're all constants. We're just looking at variables being our pivots. So we know in this case that we only have our 2 pivots and our third column has no pivots in it, meaning that the variable corresponding to our third column must be a free variable. So we know that z is a free variable. It is unconstrained, it can equal any value. And that is because there is no pivot in the third column, and that third column is what corresponds to our coefficients of z. So because there is no pivot in that column, that is the one that is our free variable. So this is the information we have. How do I actually write my solution in this case? Because we know that there are solutions, it's just that there are infinitely many. What I would do is any variable that you have that depends on the free variable, I would write it in terms of that free variable. So if we look at this top equation here, I have x plus z is equal to -6. Now z can equal anything it likes, and x is going to depend on whatever particular value you pick for z if you are looking for a particular solution. So always write each variable that depends on a free variable, write it in terms of that free variable. So I would have that x is equal to -z minus 6. I just rearrange it so it's in terms of z. Y is a constant, and z is equal to any value. It's a free variable. So whenever you get this kind of a problem, this is how I would approach my solution. Any variable that is in an equation with that free variable, write that variable in terms of the free variable. Any variable that equals a constant, you just write it as a standard unique solution. And then any variable that is a free variable, you just say it equals any value. You could go on from this and say, okay, this is the solution. There are infinitely many of them, depending on which particular value I decide to use for z. It can then ask you for a particular solution. In that case, all you would do is pick any value you want for z, let's say 1, and then you would determine what x was depending on the value of z that you pick. So if I picked z is equal to 1, that would make x -7. So a particular solution to my problem would be x is equal to -7, y is equal to 5, z is equal to 1. That is just one particular solution, but there are infinitely many of them depending on what I picked for z. So to sum up, what do we do if we have a system that cannot be put into quote-unquote diagonal form, where you've got ones on the diagonal on the left-hand side and then these constants on the right? What happens if you can't get to that situation because you end up with a row of zeros somewhere on your left-hand side? The first thing you do is you apply Gauss-Jordan as much as you can. Okay, so that means trying to get as many of these diagonal entries as a 1 and then eliminating or making 0 any entries below it that you can. Okay, so try and go through this as much as you possibly can. You may end up coming to a situation where you have to skip over a column because there is no particular pivot in that column, so you then have to go to the next column over in a particular row. So you're just going to carry on. If we, for example, let me come back to here. If I ended up with, I had 3 equations and 4 unknowns. Okay, let's say I still had these 3 equations, but I had an extra unknown in there. I could end up with a situation where if I had w, x, y, z as my variables, w, x, and z could be variables that aren't free variables, and y could be a free variable. Well, I would have to jump over that column because I would basically just end up with zeros where I would have a pivot in that column, and so I would have to go over to z and look at its pivot. So it's always looking at the leading term, which is where I'll come to in a second here. You're always going to look at the leading term in any particular row. That is the first non-zero entry in that row. So you apply Gauss-Jordan as much as you can, and then the second thing you're going to do is make each leading term which is just the first non-zero entry. In each row. A 1, and make everything below and then eventually above it when you do backwards elimination a 0. Okay, so you just apply Gauss-Jordan as much as you can to those leading entries. If you get to a point where you have a row of zeros on the left and then some non-zero constant A on the right, so A does not equal 0. So you get some row of your matrix that looks like this, then you know that there are no solutions to your system of equations. So otherwise, if A equals 0, so if we end up with a particular row where we've got zeros on the left and a 0 on the right, and or, either way, we have a column that doesn't contain a leading term. So these are a couple things to look out for. Or a pivot. Then we know we have infinitely many solutions. So a big thing to look out for is, do I end up with any inconsistencies? Do I end up with a row of zeros on the left and a non-zero on the right? Or do I end up with a whole row of zeros and I find somewhere I do not have a leading term or a pivot in a particular column? That would then tell me that I would have infinitely many solutions, because my system is still consistent. I don't have some inconsistency like I did before where 0 equaled 5, but I know that I can carry on to have infinitely many solutions. I'm going to do one final example here with infinitely many solutions. So this time I'm going to have x plus 5y plus 3z is equal to 9, and 2x plus 9y plus 7z is equal to 5. Again, I'm going to put this in matrix form to make it slightly easier to deal with. And I'm going to use Gauss-Jordan as much as I possibly can. Again, you can put this into a calculator, either to show what you've done is correct, or if you do not need to show your work, you can just plug this straight in. I'm going to go through and do this just so that we can see what happens. So I've got a 1 in that top left entry, we're good to go there. I now have to make this term, that 2, a 0. So I'm going to do row 2 minus 2 times row 1. Row 1 remains the same. That then becomes a 0, and I get -1, 1, -13. So my new row 2 is my old row 2 minus 2 times row 1. Now I have to multiply my row 2 by -1, because I've got a -1 here and not a 1. So my leading term is not yet a 1. So we need to multiply that entire row through by -1, and that will make that leading term into a 1. Okay. We're now out of rows. Okay, so we've done all the forward elimination that we could possibly do because we have no more rows that we have to worry about pivots or eliminating anything below a pivot. What we do have to do is we have to worry about making anything above a pivot a 0. So I still have this 5 here that I need to make into a 0. So to do that, I'm going to do row 1 minus 5 times row 2, and that's going to give me 1, 0, 8, negative 56, 0, 1, negative 1, 13. Again, I have no pivot, no leading term, in my third column. Okay, I don't have any row where my first non-zero entry lands in column 3. There is no leading term in column 3. There is no pivot in column 3. So that tells me that z, again, is a free variable. My system's consistent, so I know now that there are infinitely many solutions. So again, what I'm going to do is write these out as equations, and then anything that depends on that free variable, I'm going to write in terms of that free variable. So if I write these back out as equations, I get x plus 8 times z is equal to negative 56, and I get y minus z is equal to 13. Z, I know, can equal any value because there is no leading term and no pivot in that particular column, in that third column. So it can equal any value. We know it's a free variable. So now I have to write x and y in terms of that free variable. So that tells me that x is equal to negative 8z minus 56. Y is equal to z plus 13. And z is equal to any value. Again, if they ask you to write down a particular solution, you just pick any value you want for z. So for example, you could pick z is equal to 1, and then you would figure out what x and y are for that particular value of z. So it's completely up to you what value of z you pick, unless they give you a specific one that they want you to use. But that is just a particular solution to the problem. So it's one specific point, but there are infinitely many points that can be classed as a solution to this problem.